You've got to have a mix of all these things.
Papers faster, because people cite papers at the moment, altmetrics, they tweet about things and they write about things, whereas people don't necessarily cite non-traditional research outputs yet, but we can still go out and grab the altmetrics.
Yeah, I think altmetrics are in a really good place at the moment to apply to data to help us do what we need to do, because citation counts, yeah, it's not designed for data. Altmetrics, we are in the situation where we could possibly kind of tweak it and make it more suitable for data. And altmetrics is more likely to be able to answer that question of how people use data than citation counts are.
Thank you. I have no idea what I'm doing on the computer here.
I have no idea what my talk is either, so it makes two of us. From
We've broken everything else. It's just PDF.
Yes, it's PDF. Command F. I know I have that enough. I can do
Very good. Okay.
It's a bit stretched. Okay, I didn't start moving it. Anyhow, I'm not going to talk exactly about what you want to hear, but I hope I'm going to talk about something which is relevant to the where we bring up metrics when it comes to tracking something else. I'm going actually to repeat quite a few figures Sarah discussed before. So I work at CERN. Who knows what CERN is? Okay, this makes it easier. So we have taken about 10,000 people, 10,000 scientists and engineers for some, I don't know why they restarted the thing here. This is not going to be just because, sorry, all my slides have something written on the bottom, so if we have something on the bottom,
you can move it. Move the mouse over. Move. It should go away.
Yes. Anyhow, it has taken a large amount of people, a large amount of time to build a very big machine. That, I'm sorry, I'm nervous by this thing because we want to do something that. So we are going to scroll like that. It will take a large amount of people, a large amount of time to build a very big machine with which we do physics. And one of the results of our physics research has been very recently to discover the Higgs boson, as you might have heard. This is not a very different kind of scientific output than other scientific outputs. It's in that what we've done after having discovered the Higgs boson is to publish a paper on the discovery of the Higgs boson, which looks like every other scientific paper, so I'm not speaking about data yet. That's what the scientific paper looks like. On page number 4, there is a small green blob, which means that we have discovered the exposure. There is a small thing that makes this paper look different by other papers, and I'll come to that back later, which is the distribution of pages and authors. After having written this paper, what happens is that somebody else has got a Nobel Prize in Physics, which is Professor Higgs, which 50 years before theorized the existence of Higgs. Why am I saying 60 years? Because actually, on Monday is our birthday. Monday turns 60, which I've been there for almost half of the time, so it makes you realize that 60 is not so much. That's a bit scary when it gets to that. So, with 60, this is actually something which is relevant for what I want to say today. 60 years ago, actually 61 years ago, there was the first convention which was written, which was giving CERN his mandate, what CERN had to do. You start to see how the world was different 60 years ago. They didn't have any laptops, or like laptops, even somebody was smoking in the room, and these are our founding fathers. And by the way, the man there in the corner, François de Ros from France, passed away earlier this year. He was 103. And he came 2 days before passing out to give actually his last speech at CERN. So he has seen the 60 years history of CERN. What our convention says is that the results of CERN, remember this 1953 was a very strange time of the world in Europe, the Cold War was ramping up. The results of CERN of this experimental and theoretical work shall be published or otherwise made generally available. What does it mean for us to make our result generally available? On the one hand, it means open access to papers. Next year, we should reach 90% of gold open access to our scientific outputs, and we are aiming for 100% by the end of the mandate of our current CEO. But this is not this conference, this was last week. This conference is about data. What does it mean in the field of data? What does it mean to make publicly available our raw data? We take, that's what a collision at the LHC looks like. The one of the Higgs before was nice, clean, with nice line. Most of what we take is this kind of crap. And we take about 25 billions of those every second. So you cannot save 25 billions of those every second on tape. You only save 100 of those every second on tape, which still makes for 100 petabytes of data on tape. This is not the kind of data you can shave. It's not the kind of data that makes any sense to publish, let alone track. Is actually this data any useful? As it turns, it depends useful for whom. The reason I showed you the 3,000 names on the paper and the picture of the theorist who has got the Nobel Prize later on, is that there is a secret tension in this discipline about having an idea and verifying it, and then checking if your data actually makes sense or whether there is somewhere else. I don't even want to start speaking of the new theory of the landscape. Freak you out. We are just in one universe, or infinite parallel universe, and we cannot talk with the others. But data like the data that are there can help you figuring out whether traces theory are working or not. And this is a job of most of the community, which are theoretical physicists. What the theoretical physicists need is not something like that, nor something like that. Actually, they're very happy with pen, pencil, and electrical and chalk. What they need is something which is very basic. They need the small bank that I showed you on the 3,000 author paper before, which is this figure, and they just need this figure in very simple, stupid numerical format. And this is, if you print it, that's actually 20 pages of text. So from 100 petabyte on tape, you need to go to 20 pages of text. Point is, and this is very similar to other disciplines, is that there ain't no infrastructure to share these 20 lines of text. If you know somebody, you're going to get the figure in text or form and you're going to use it. But this defies the entire purpose of open sharing of knowledge and make our results publicly available. So we have, with our small open data team at CERN in the last 2-3 years, been working very close to the experimental collaborations and to the theory community to understand how we could work together to help them share these results of research. The tool that we have used is this one. This is also called Inspire, but it's another Inspire, with what Sarah was saying. That's the digital library we operate at CERN together with partners in America and China, which serves scientific information to our discipline. So it's a discipline-closed system. We have 1 million bibliographic records, 500,000 of them is open access full text. We have 20 million citation triples, and we have fully disambiguated about 20,000 authors. We have 50,000 users, which means every living and active physicist in this field uses this system, and we have about 2 searches per second. You can do interest science with this. This is the searches per second. The searches in Inspire as a function of time. So I can demonstrate that half of the physicists, this is lunchtime, this is night. So half of the physicists work overnight, and 10% work all night long. Nobody ever measured that. So it's true that 10% of the physicists work overnight. So if everybody uses this system, you can do something interesting, which is to use this system as a force for good and as a platform for open data, for data sharing, for data publication, for data citation, and to try to bring around all the items that the speakers before me have been discussing. Let's see how we make this work. That's what an article looks like. That's the discovery of the Higgs boson article. Very boring. There is a button there which says show all the 2,923 authors, which you don't want to click. There are the citation. By the way, somebody before was mentioning that we don't own the citation. Actually, we own the citation. We text mine everything, and the citation are free there to be downloaded. We know who cites this paper, how many are self-citation, and we have the co-citation method to allow navigation. And very recently, by the way, you might note that all the other screenshots you have seen are beautiful. The screenshots of the publishing industry looks totally beautiful to see papers. We have to work very hard to make this look ugly, because our community wants us to reconstruct the look and feel that it had in 1993. Because this, the predecessor was actually the first website in the US and the first database on the web. And I'm so old to have the original email in my inbox from Tim Berners-Lee when Tim BL, when it was announcing that this database exists. So it looks very ugly, and there's something new now, which is a tab over there which is called Data. If you go on the Data tab, there are a few data sets. If you go on a record on a data set, you get on the record, where you see something which is being shown also before. There is a data set which has authors. You can show all the 2,923 of them if you wish so, as a DOI, and you can click and you can get the data out. So that's what we have done last year. What has this implied after 1 year? What has happened? What have we observed? The first thing that we have observed is that the theorists, they lied. There's a tweet from one of these people trying to reconstruct and interpret this data, and was saying that getting the data on Inspire is like a day you ask for a pony and somebody gives you a unicorn. And if there was one good reason to get a Twitter feed, a Twitter presence on Inspire, was to just get this tweet in our box. The second thing that has happened is that we have put a data set DOI to this data set. What has happened? And we have done nothing. We just left it in the wild. A bit at a time, things have started popping up and creeping out. Now, every year in Inspire, we ingest between 50 and 100,000 records. We text mine and type text to spot references, and we create all our reference citation networks. So we have trained our machines to recognize a citation to a DOI of a data set that we have, and sure enough, what happens a little bit at a time, that 5 citations have suddenly popped up for this data set. And the data set has been cited 5 times, has been co-cited with this record, which actually is interesting because it lets you understand what people read when they use this data. And without any intervention from our side, this is what a citation looks like. It looks like exactly, we have done a suggested citation, Atlas collaboration data, and the link and the DOI, and people do it. Fine, only 5 papers have done that. But this has happened there in the wild, because all the steps that we have laid out, all the pieces of the infrastructure, became so obvious and invisible that this is coming up. And then something fun is arriving, that people come to us and say, wow, it was cool the thing that you did with data. You know, I also have some data. I'm a small team. I don't have an LHC in my garden, but I actually write code, and people might use this code. Can I also get one of these numbers where I can be quoted? And we are getting this now about once a month. Now it's getting once a week. Somebody's coming and asking. You see, since we are a community aggregator, everybody lives in this system all night long. So this is happening in the wider world. And we had a ad hoc solution. Somebody came and said, I have this code on GitHub. Can I put it in my paper in Inspire? Yeah, sure. We did an intermediate step for another platform that we run as which is Zenodo, and we now have a record inside Inspire where the software of these persons with a data site DOI, which is not from Inspire and Zenodo, exists. So those two authors, they can represent the integrity of their scientific contribution in a single place. And that's exactly the key that we are observing to get scientists on board. I have not had much to think about scientists and what they want or what they want to do yet this morning. How do you get scientists on board? What is a scientist? What is an author in our field? So I can introduce one author. It's one of the persons we are working very close with, is Professor Kramer at NYU. So what Kyle is, if you click there, is 3 pages down. But one interesting thing is the person who had worked on this additional piece of software to analyze some piece of this data. Now, the additional piece of software to analyze some piece of this data is just 2 of those authors. The rest is 3,000 of them. So what happens when you click on his name, you see one particular feature that we offer in Inspire, which is, again, everybody's in author profile. There is a difference in the author profiles that we present, is that this is how people get hired in our discipline. Because if everybody uses this system, every hiring committee uses this system. And when you look up for somebody, you tend to look up for the person, and then you look for the paper. We launched this 3 years ago, and it's the single most used feature that we have. So this can be a force for good for the principles of data citation and for trying to build pieces of infrastructure, because after all, people think about people. We are sociable apes. We are not machines that look at data, even some of us are. 2 things. The first thing is that we present usually here who is this person. Of course, there is an author link, all the citation summaries to all the papers that this person has ever written, H indexes and everything you want. This comes higher, this H indexes that also you can get anywhere else, because you also have pre-publication. So since numbers are higher here, everybody's happy. And then the central page, there are all the publication of the person. The first step that we've taken now is that in addition to all the publication of the person, now we can show all the data sets and code and additional kind of material that this person has produced. So we have already addressed the fact of generating visibility for the scientific outputs of somebody, whichever those scientific outputs are. The next step that we are about to take, but first we want to build enough data sets not to look like we are serving a special interest, is to update the part on the side there. Because there I have all the citations of all the papers of this person, and all the conference papers, all the books. What I can do next there, it's really weird to flip the switch, is to have all the citations to the other stuff that this person has done. This is your software, this is your code. The moment in which you do that, you have generated a closed market, demand and supply in a closed ecosystem, and everybody will want to put more data and more papers in, because it shows up in the place which is used for hiring, assessment, and just narcissism as well. And of course, once you click on the ORCID profile here, you go on the ORCID profile of Hive and you find the data of the list. So we have closed the loop in this particular context. And those slides, it looks like I'm talking about something else here. I am not talking, and I have not talked about how do we use altmetrics to figure out tracking of data. I don't know how often those data have been tweeted about, blogged about, or they've appeared in any other kind of platform. I know how often the stuff is downloaded, and I tell you, if your own system to be gamed, these numbers stay in our logs, they don't go out. So what I've talked about here? I talked about something that the scientific community seems to want, which is to ask us, can you take data and code and make them look as papers? Can we have more of the same? And which is bizarre, because it's exactly the opposite of things we are talking about here, which is how do we measure stuff in a different way. And the request of the scientific community was, can we measure all this new stuff like we used to measure the previous one? This seems to be a bit of a settling note to close this, And therefore I show another bit. Sky himself, in the moment in which we have all these scientific outputs out there, including the data, it's not very difficult to pull out the feed of all our DOIs. So it's not very difficult for him to build an arithmetic widget to everything he has. He used it to build an arithmetic widget about all the papers he has in his file, and now he can build an arithmetic widget through our connection to Orchid for all the data that he has there. So I guess that the lesson this gives us is that not every scientific community is ready to use different ways to measure things. And actually, the different ways of measuring things can scare people off. But if you slowly build a platform for things to gradually evolve, starting from an existing mental model into the new one, then people are going to run after you to say, can I have more of the same, please? Thank you.
Salvatore? No, between you and lunch. Yeah, awesome.
I'm always impressed what hydrogen physics folks do. How can other disciplines apply this? And you have a very closed world and one central system. But how does that work for social sciences, biology, whatnot, which is much more disparate in very different places?
We had nothing of these 2 years ago. We had zero of these. Then we set up this fantastic team, the acknowledgement started on there, with this release to run our open data team at CERN. And what we did was to start listening to people and ask questions. So if you listen what people want, you give them what they seem to need, they seem to work for us. Now, you don't need to be a physicist, or you don't need to be a CERN in order to ask people what they really want in terms of deliver this to them. And sincerely, I do believe that platforms like lots of the larger publishers we were discussing before, they are in an even better condition to affect, take on, and social trends, because we have only 50,000 people on our platforms. We have enormous numbers more. If any, it is a limited part. Just try to understand what people want. There was another hand which flapped up before, but I don't know from where.
Okay, so we'll focus on lunch. And everybody there. I think we're going to run over at the end, so we might not have time to grab everyone together at the end, so do grab Salvatore afterwards. But up next, hopefully, Kat, you have the computer down.
Should be all right.
Okay.
Yeah.
Thank you. So let's see. So I'm going to probably come in between these two talks in terms of talking about a little bit of metrics, but maybe not a huge amount of metrics. But I'm going to talk about things from the point of view of software. And I guess first, is Simon here? Can you put your hand? No Simon. Okay. Sorry, I was going to put an elephant figure on this picture, and then I didn't. And so I just wanted to see if anybody here was going to be upset.
Okay.
But I guess not.
Yes.
Okay. Okay, very good. Thank you. Okay. Sorry. Let's see. So Simon in the National Science Foundation and the Division of Advanced Cyber Infrastructure. And what we do, basically for anyone who doesn't know, yeah, this is amazingly small, is to fund, to help promote the progress of science and to advance the national health, prosperity, and welfare. We have about $7.2 billion that we spend. About 95% of that goes out to external entities to do research, and a little bit of it is used internally for process. And we fund 24% of all federally supported basic research at U.S. colleges and universities. And, in many areas we're the primary funder. In some cases like mathematics, it's something like 95% of the research funding comes from us. So this is just a quick view of what we do. I know you can't see this very well, I can't see it very well, but basically it's kind of biologic sciences, education, engineering, geosciences, mathematics and physical sciences, and social sciences, more or less. And the one that I left off in the middle is computer sciences. And so that's where I fit in. Well, this looks really horrible here. I'm this third slide down, which is the Division of Advanced Cyber Infrastructure. And so we think of ourselves in kind of two roles. One is that we fit into computer science because we're taking a lot of computer science tools, but we really try to span across all of these areas. because the cyber infrastructure that we're developing is something that should be of use to everybody, and it's components that are coming from all these different areas that are what together builds up that cyber infrastructure. So specifically what we do is to support, coordinate, and help acquire and provision state-of-the-art cyber infrastructure resources, tools, and services, try to support research and creation to make the cyber infrastructure better over time, and then serve the community of scientists and engineers across all disciplines to make sure that they have the infrastructure that they need to do their work. So I keep saying cyber infrastructure, so here's the definition that I like. Computing systems, data storage systems, advanced instruments and data repositories, visualization environments and people, all linked together by software and high-performance networks to improve research productivity and enable breakthroughs not otherwise possible. So sometimes this might be an e-science infrastructure or e-research infrastructure or something else like that. But sometimes when people say those things, they kind of leave off the data and the software and some of the other pieces. And so cyber infrastructure is really meant to be a pretty inclusive term. So software is one of the things that I mentioned as infrastructure. And so we have a bunch of clusters in my division. I'm running the software cluster. There's also a data cluster and an HPC cluster and a couple of others. And I would say that I'm going to talk primarily about software, but I think most of the things that I'm saying also go for data in one way or another. So software is, I would say, is the thing that actually fits between science and the computing infrastructure that actually makes the science possible to do in terms of computational science. And at some point I was looking through Science magazine and looked through a few different issues and noticed that about half of the papers seemed to be software intensive. And of the ones that weren't software intensive, many of them had pretty large software components as well that really made them possible. I think research in science in general is becoming more dependent on advances in software. Significant software development happens across NSF in a variety of domain-specific areas as well as computer science areas. And there's a wide range of software types from system software to applications, modeling, gateways, analysis, algorithms, middleware, libraries. Software is not a one-time effort. It has to be sustained. And it involves development and production and maintenance, and all these things are people-intensive as opposed to machine-intensive. Software lifetimes are long as compared with hardware. They're probably short as compared with data, but that's a slightly different issue. And software often has an underappreciated value. And so I think one of the things that I want to say about this is that for software to be sustainable, it has to become infrastructure. I don't necessarily mean that in the invisible sense, but I mean that in the sense that it is relied on. So maybe there's a way that actually maybe infrastructure is going a little bit too far. Software infrastructure projects that we have. So we think of software at a few different levels. We think of it first in terms of elements, kind of little pieces of software that are self-contained. And we've funded about 65 of these projects over about 5 years. These are often 1 to 2 PI, 3-year projects. We think then about software frameworks, which take multiple elements and put them together. The elements can be funded by us, they can be funded by somebody else, they can be open source with nobody funding them. But there's somehow larger components. And we've funded so far 4 rounds of these, about 35 projects over 4 years. And then we think kind of down on the end of institutes. And these are the things that I would say are really aimed more at communities and less at people. So how do we make software standardized for disciplines? How do we make sure that the common underlying libraries that are needed work across different software applications? How do we educate and train people to build software and then to use software? These are the kinds of things that institutes would be looking at more than purely software development. And as we go across the spectrum, the communities that we want to impact get larger when we're thinking about which projects we're going to fund. And we also want then everything to be reusable. And the slides are on SlideShare now, and there's a link that I put on Twitter, so you can leave these up later. When we have projects that come out of this process, we have a bunch of proposals, we go through peer review processes, and the peer reviewers look at software aspects of things, and they look at science impact and what they think the science impact is going to be. So I, in this kind of cross-NSF role, take that information, and then I try to do matchmaking to find other areas of NSF that want to support the software. So if we have something like a bioinformatics application that I would call a unidisciplinary project, I go to try to find the bioinformatics program officers, and they say, is this something that's important to you? And they say yes or no, and then that often leads to a funding decision, right? And we're assuming we have a good proposal to begin with. So there's something that happens before this. If I have something that's multidisciplinary, I can work with multiple program officers. In this case, I have the chemistry and material science program officers. And if I get one that's interested, then that's good enough to go forward. If I get something that's really going across all disciplines, like a web server or a math library, then I have to try to work with all program officers, and the answer from all program officers is usually, it's not really enough for me, so you should figure out if you want to fund it or not, and we do that. And so in order to actually judge the software and what all these program officers and I are doing, we have to try to understand or forecast the impact. Either understand the impact that's happened in the past or forecast the impact that's going to happen in the future. And so that's where we get into questions about how we actually do this and what the metrics are that we should be using to think about these things. So, so if you think about somebody that's developing an open source physics simulation as an example, right, we've got a bunch of different things that we can look at, from how many have been downloaded to what papers are cited and then have themselves been cited. Right? And these kind of go from easiest to measure and least value to hardest to measure and most value. And unfortunately, that's the situation that we're in, is that the things that we really want to know, we don't necessarily have a good way of measuring, and the things we can measure are not the things that are really very helpful to us necessarily. If we think about somebody that's building an open source math library, right, there's probably similar metrics, but the citations of that itself are less likely, because it's not clear who would actually cite a math library. The user of a physics application that uses the math library probably isn't thinking about what the libraries are underneath. So, and we have problems that the users don't necessarily download things like this either. They could be part of a distribution, they could be pre-installed on the system that somebody's running on, it could be part of a cloud image that they're using in their application, or it could be a service where they're not actually downloading it, they're just calling it somewhere. So, so this is what we're thinking about in terms of impacts and of measuring things that exist. In terms of future impacts, right, one of the things that we ask for in these proposals is what's the impact of your project going to be if we fund it? We don't say what the metrics should be. We let the proposers suggest what metrics they want to be evaluated against, and we use that in a peer review process to judge. Are these the right metrics? Are they going to lead to something that we're going to think is going to be successful? Right, so that's kind of how we're handling that at this point. Okay. So in the programs that we're talking about here, we work with other units to support projects that lead to software as an element of infrastructure. One of the issues is the amount of software that's infrastructure grows over time, and that's growing faster than our funding, which is more or less flat with inflation at this point. So the question comes up of how can we ensure that the software infrastructure that we need continues to appear without us actually funding it all? And the answer to this is incentives. Right? We want other people to want to do this, not because we're paying them, because there are other reasons that they're going to do it. And the question then is actually, how do we do that? So, so we're talking in other forums, and in particular this effort called WSPI, which is working towards sustainable software for science, practice, and experience, which you can Google WSPI. I picked an acronym that nobody else had picked, so Google actually does very well with this. We've had 2 previous workshops, and we have another one coming up at SC14 in November. And so if people are interested in thinking about basically how some of these things happen, I'd be very happy to have more people come to this. The lessons that came out of these initial workshops, I think probably 2 lessons that I wanted to highlight. So one of them is that many of the issues that seem to occur in developing sustainable software are social issues and not technical issues. And so we need to think about this in a cultural sense more than in a technical sense. And the other is that software work is inadequately visible in the ways that count within the reputation system that underlies science at this point. Right? And so these are really the things that we're thinking about. Okay. So I've had a few little things in red rectangles. They've actually been these 4 things primarily. Right? So we need to be able to forecast impact in order to judge software. We have to try to make sure that people want to produce software, not just because we're paying them for it. We have these problems that these issues are social in many cases as opposed to technical, and we have the issue that software work is not visible enough in the ways that count. And so we have a hypothesis that's come out that says that better measurement of contributions can lead to rewards or incentives, which can lead to career paths, which can lead to willingness to join communities, which can lead to more sustainable software. And so this is really what we're trying to do, and this is all derived by, basically started by having better measurements. So I don't know what these measurements are necessarily. This is part of the reason I'm coming here, is that I want to get people that are interested in this really to think about what the metrics should be for software. Actually, I wanted to just mention one quick thing based on the previous talk. There were a group of people at NCAR, which is the National Center for Hemispheric Research in the US, that decided they wanted to try to get people to cite things that they were producing. And so they suggested that people cite their computer system when they used it, and they cited some data sets when they used those data sets. And they did a study then, over a year period, I think, about did people actually do this. And what they found was that about a third of people that they could find did cite them, and they cited them as citations, as endnotes or footnotes. About a third of people didn't actually use the language they suggested, but instead put something in their acknowledgement statement, saying that this is something they used. And the other third of people didn't do either of those things. They put something just in line in the text saying this. And so the NCAR folks were able to basically do a lot of text mining and find these things and determine what had happened. But they weren't really able to encourage people to do what they wanted. And so I think that's an issue that we have to kind of think about, is how to actually get users to do this. Okay. So we're trying to do a few different things moving forward. As I mentioned, I'm very eager to have ideas from this audience and from others. From the point of view of NSF, we put out a Dear Colleague letter, which is basically kind of like a reminder that we have programs available that people can apply to. And we basically were asking for people to study norms in supporting scientific discovery through practices for software citation and data citation. And what came out of this is we have 6 eager projects, we call them, smallish projects for 1 to 2 years that have been funded, and 3 collaborative workshops. And so we'll let those go for a year, see what happens, and see if they actually lead to results that are big enough that we build a larger funding program out of, or if they just lead to results that we say, okay, this is the results, and now we know what to do with them. But that's where we are there. I'm also thinking about this as a researcher. So I'm thinking from the point of view that I would like to see a system where products are registered, and I would call products software or papers or data. When they're registered, I would like to imagine that people can create a credit map for those products, which is a weighted list of contributors, and contributors here are authors, acknowledgements, citations, anything else that's used. I know this is difficult, and we've had a lot of discussions about if this is really possible or not, and I'm not sure the answer to that, but it's an idea at this point. A DOI or something like that would be an output that goes with this. And this leads to this idea that I think is actually fairly important in transitive credit. And so there's one paper that I wrote just about this idea, and then I've written a recent paper with Arthur Smith that tries to figure out a little bit of how we might implement some of this as well. So the idea here is that if paper 1 provides 25% of its credit to software A, it registers that in the credit map. And then software A previously had a credit map where it provided 10% of its credit to library X. Right now we can see that library X is getting credit for paper 1. Right, and that's the thing that I'd like to be able to do through provenance, through something like this. I don't know exactly how, but all the stuff that's indirectly being used doesn't really get a fair shake at credit at this point, and I'd like to figure out ways to encourage people to do those things underneath. So this helps developers show that my tools are important. There's a bunch of issues that I really don't have solutions to at this point. So one is trust in the person that registers a product to do the credit map in a way that's happy for all the people that have contributed. And I think we've kind of know some solutions to this to some extent. This is the discussion that has to happen with paper authorship listings. And there's a process by which most authors end up being happy with the way that's done. So I think this is kind of a social thing that we can do. Technologically, how do we actually record this, and how do we register it? Can we do this on top of the DOI system? Can we do it in a separate system? Right? How does the metadata work? Are there standards? So there's a lot of questions. I'm really just bringing this up as an idea that I think is worth exploring. The community as a whole, and here I guess I'm speaking to some extent about the people that have been coming to some of the WISPY events and communicating through that, are asking questions like, is there a role for non-tenure track researchers who produce software or data in universities? And everybody seems to think the answer should be yes. And then the question is, do universities recognize and support this? And most people would say the answer today is no. And so then the question that comes along is how to get universities to do this. And my feeling, and the only answer that I've had from people, is that if we take the young people that believe this and we wait 30 years, they'll be the older people that'll be running the universities. I think that's probably true, but I'm hoping that we can do something that's a little bit sooner. And the question is exactly what. I think actually in the UK there's probably been a little more progress in this, and maybe it's because of the funding model for universities and that things are a little bit more centralized in some ways. What's needed to support reproducibility of science in terms of both data and software is, again, are more questions. I think there's a lot of entities that have similar interests in software and data. Research councils here, NIH, DOE in the US, the Sloan and Moore Foundations in particular have been doing some interesting things with trying to get universities to change the models that they're using and try some new models for supporting data. Mozilla and Apache Foundations, for example. And I guess I didn't mention things like Crossref and Vivo and other things, or Castrate, but there's a bunch of other things as well, RDA. So I'd like to encourage some participation in WISPY because I see that as an opportunity to think about some of these things and to talk about them. And other ideas and questions are also welcome now or in the future. I have some email addresses there. There's a Twitter handle that I've been using as well that was on the first slide, and you can find me there. Just quickly in the slides, there's a bunch of links to different stuff that I've talked about that people can look up later. And there's a lot of different people that have been involved in working in different parts of this and coming up with some of this. So just leave that there and say thank you.
I think that was a good summary. We had at the beginning looking at how altmetrics and how these non-traditional research outputs, then we said maybe altmetrics aren't ready, there's areas that aren't ready for altmetrics in non-traditional research outputs. And then we saw how things like the credit map can help track things better, but again it seems to focus more on citations and how you apply that to altmetrics. Does anyone have a quick question for Dan at the moment? Yeah, about that.
How do you find the limits of what it questions?
Right. So the question was about the credit map and how you define the limit. And so I think the thing, because of this idea of transitive credit, you only have to worry about the things that you're directly using. Anything that's indirect, you don't worry about because the direct users have already recorded those things in an ideal sense. So then the question is, of all the things that you're using, how far do you go? And I would say anything really that you would put in a citation list or you would put in an acknowledgement statement today in a paper are the things that you should be thinking about.
Only in a paper? Who's tracking this?
Sorry?
Should these people not get credit for helping in this way, in this presentation?
So most of these people actually are in papers, so they would. And the other people, yeah, so these are the people that I would acknowledge that this was a paper on the top, and the people down on the bottom actually are paper authors, so yes.
Good stuff. And over.
Can I just ask a follow-up question then? So
Yeah.
in the same way that in good academic practice, these current researchers do record basically from day one everything that they read and their response to us and any notes they take, etc. Are you suggesting that software should be dealt with in a very similar fashion?
Yes. Yeah, so I'm suggesting that both software and data should be dealt with in a similar fashion. And I think one of the issues that comes up with this is that it's not clear to me that it's practical to do that using the system of taking notes and then kind of going back over the notes and trying to figure out which of these things led to this paper. So I think we really need systems that do this, particularly for electronic information like software and data. And I'm actually hopeful as we move forward to provenance systems that really do more tracking of workflows and let you kind of go backwards and forwards over different ideas, that some of this can automatically be extracted from those. One last question?
So I'm fascinated by this idea of creating a citation list for software. I think people think they should be able to just follow imports required and put together a citation list for it. But if you're going to get something really bizarre, like, and maybe it's perfect, like NumPy, it's going to be like in everything, right?
Yep.
Is that, that? I mean, it really has had a huge impact.
Right. I think that's actually, I think that would really be good because I think that stuff like that isn't getting the credit that it deserves.
But then does Guido get credit as well?
I'm sorry?
Does Guido get credit as well? The person who wrote Python?
So in theory, NumPy would have this credit map of their own, and if they chose to credit Python, which I assume they would, then yes. Because this keeps, it keeps going down, right? It's the turtles.
Turtles all the way down.
Yeah.
So thank you once more to Sarah, to Salvatore, to Dan. It's interesting that standards is going to follow on this after lunch, but we've already overran it, so I really enjoyed that.